At 65.7 degrees in my basement laboratory, it's an excellent day for flying. But I'd like to begin this video with two passages from Anderson's Introduction to Flight. He was discussing the progress of the Wright brothers after they had refined their airfoils through wind tunnel testing, and they developed a method for controlling bi-wing flight of their kite and gliders through a method of wing warping. The single design challenge remaining had to do with power, and I quote, "Heavier than air flight was inevitable once a suitable power plant could be developed to lift the aircraft off the ground. It was just a matter of developing an engine having enough horsepower while at the same time not weighing too much." It was the Wright brothers' custom-designed and constructed gasoline engine that was responsible for lifting their Flyer 1 off the sands of Kill Devil Hills that fateful day in December 1903. Now, we've established that with orthosonic lift, an airfoil is not required. The effect was powerfully demonstrated when we oscillated air particles over the upper surface of this flat pine slab. But to do so required me to use this large low-frequency driver, which at 1138 grams was over 10 times the mass of this wing. Clearly, Anderson compels us to ask the question, does there exist an acoustic engine powerful enough to lift more than its own weight? And that's the question we're going to try to answer today. We'll employ a sine wave at 83 cycles per second, and it will drive a single channel of this audio amplifier. And we'll monitor power on this meter set to match the 8 ohm impedance of our driver. We'll be operating at around 15 watts, partway between this mark for 10 watts and this mark for 50 watts on the upper logarithmic scale. 2 LEDs will brighten as the needle moves partway past the 10 watt mark, like this. Now let's compare two low-frequency audio drivers. This standard design has a maximum power capacity of 15 watts, and it can run continuously at about half that. This modern design can handle about twice the power, though it's lighter and more compact. What's the difference? The standard speaker design uses for its permanent magnet this gray ferrite ceramic ring encircling the voice coils inside. It's potter's clay with a high concentration of iron oxide called magnetite, which is inexpensive and readily cast into any desired shape. The downside is it's rather heavy, with this driver weighing in about 312 grams. Now the magnetism is substantial. This steel bolt is readily supported by it, and if I'm careful, it'll support the weight of the entire speaker. By contrast, the magnet for this modern design is an alloy of neodymium, iron, and boron. It typically has 22 times the magnetic strength per gram of ferrite. That makes it small enough to fit inside the voice coils, centrally, in this shiny black enclosure on the back. That enclosure also acts like a magnetic shield, so when I put the bolt there, it rolls right off. That makes this speaker safe for use near computer hard drives. It won't erase the data. In addition, it concentrates the magnetic field in close to the voice coils. So we not only have a more powerful driver, but a more efficient one. And it weighs in at about 138 grams, less than half the mass of the standard driver. And that includes the mass of this flat cardboard wing I've glued to the front. It was cut from an ordinary tablet of paper's backing. Now that means This wing is not an airfoil. Remember, orthosonic lift prefers a nice flat surface. It also has no angle of attack, so we've eliminated the two major causes of aerodynamic drag, turbulence, and even stall. Now, the outside diameter of this wing is about 6 inches, and I've cut a 2.5-inch port inside centrally to let the sound through. Now I'll take this aircraft and set it underneath this particle board deflector, and we'll move the camera out front so that you can better view our experiment. Here's our sine wave, and here's our power. And this is orthosonic lift by radial deflection. Power down, and she drops. Power up, and we have lift. Sound emerges from the port and is deflected by this surface. The result is oscillating air particles radially in all directions across the wing. The moving air on the upper surface offers a lower pressure than the still air underneath, from which we derive lift. I call it orthosonic lift because the direction of the lift is perpendicular to the sonic flow across the wing surface. It's obvious to me now that Anderson was indeed correct. Once we've identified an engine capable of lifting more than its own weight, heavier than air flight is inevitable through the lifting mechanism, in this case, orthosonic lift by radial deflection. Power up,